Okay, I'm going to draw an x and y coordinate system again. No, I'm not. I'm going to choose my pen. Blink blonk, blink blonk. I'm going to draw it in red, and that's a generic y equals mx plus c curve. I don't really know very much about m and c at this point. I know that c is positive because this intercept is above the axis, and I know that m is positive too because it slopes upwards. What I'm going to do is to identify a couple of points anywhere along this line, x1, y1. This one here is x2, y2, and they're just 2 points on the line, not on top of each other. And I'm just going to fool around with it. We've got these points. So we know that the line is y equals mx plus c. So in particular, y1 equals mx1. I'm leaning on that. That's what the problem is. x1 plus c. That's there. And y2 equals mx2 plus c, which is there. And I'm just going to fool around with these two equations. What I'm going to do, see how I write this out, and then I take the special. This is the case for any point on the line, and these are these 2 points I'm interested in. Okay. What I'm going to do is to subtract that one from this one. So y2 minus y1 equals mx2, which is that term there, minus mx1, which is this term here, plus, in brackets, c minus c, because it's that c minus this c, and of course that's equal to 0, so these guys cancel out. I'll write that out again. y2 minus y1 equals mx2 minus mx1 equals m times x2 minus x1. y2 minus y1 equals that. So m equals y2 minus y1 upon x2 minus x1 divided by. I've done quite a lot of work there. I've taken this guy down to the other side and then written it the other way. That's quite cool. I'm going to surround that in green because that's quite important. And I'm going to write it out here again in green because I feel like it. Y equals, no, I got it wrong. Green. M equals y2 minus y1 over x2 minus x1, which we got just from fooling around with the algebra. What I'm going to do is to see if I can express that geometrically by taking these 2 points on the line and joining them together. These dotted lines here are exactly vertical, parallel to that line, and this one's exactly horizontal, parallel to this axis here. And observe, this distance here is just y2 minus y1, because that has got a vertical distance of y2, and this one, that distance there, is y1, and this whole distance here is y2. So what's left after you've subtracted out that one is y2 minus y1, and the same logic tells you that this is x2 minus x1 there. It's getting a bit crowded, that diagram, so I'm just going to draw that again down here. This is your line. It's not very neat, is it? But there it is. This is y2 minus y1. This distance here is x2 minus x1, and that's a right angle, I guess. So that's interesting. That tells me that y2 minus y1 is always proportional to x2 minus x1, and that kind of makes sense. For this is for the same line, so I can draw that little triangle anywhere I like. It doesn't matter how big it is or how small it is, or whether it's huge or overlapping another one. No matter where it is, each line, that distance there, which is y2 minus y1 for this particular pair of points, divided by that, they're always in the same ratio. So these guys here, these triangles, are what you call similar triangles. They're all exactly the same ratio. And so I always imagine myself cycling up a hill. Let's see if I can draw a bike. What does a bike look like? Saddle, handlebars. Oh, I'm not an artist. There's my bike anyway. So I'm cycling along up here, And so if I know the ratio of that distance that I've climbed here versus this horizontal distance here, then that gives me the gradient. That gives me how steep the curve is. So quite often I will talk about m equals the gradient of the line. Okay, because it's like a gradient on a curve, or on a road. It's just the same deal. Okay, so that's a nice little way of expressing what the slope actually means. It's how steep it is. And I'll play with wherever. That's 5 minutes already. I'm going to have to stop there, but I'll cover a few more cases later on. Okay.